So we will start from team 7, and 7, 8, 9, 10, and team 1. 5 teams will be presenting today, and each team has 15 minutes, including discussion. So please stop before 10 minutes. You can present up to 10 minutes. All right, any question? No? Then we can move on to team 7. We have a presentation material right here. Okay, go ahead. 죄송합니다.
시작하면 될까요? Hello, my name is Yunshik On, and I now presentation about the final presentation for Team 7, and our topic is the high protein. This is the context of the last project presentation for the floating island. We did 2 tasks for the design of the floating island. We figure out the design factor for the floating structure, for like mechanics and where to site, and we also analysis of the existing structure. In the midterm presentation, the comment is as follows. The main is the where we insert the floating island and the suggestions of the combining floating and fixing. We focus on this comment for our final presentation. The context is as follows. First, we select the location of the floating city where can be guaranteed stability. Second, we define the mathematical model for the floating city for the installed mooring line. Finally, we show our challenge and suggest the simulation method for the floating city's design. Selecting location of the floating island is much more complicated than just placing the ship or our other wind turbine. Multiple elements such as environmental concern, wind profile, and nearby ocean and commercial aspects must be considered. In this project, to consider all aspects, we will look at the data of the wind flow, commercial routes, and sea depths for stability to select the best location. To avoid disturbance on the sailing ship, the floating installation not installed on the ship route. As you can see from the figure, there are less ships in the recommended area 1 and 2. This means the floating island can be installed at the location without disturbing the ship movement. To prevent external force from the wind itself should be less for stability. Once we consider the wind with power density and wind with speed at 100 meter high, wind at the recommended location is weak enough to the stability of the floating island. To install floating offshore wind floating island, the depth of the sea should be deep enough to height of the sea should be constant. At the recommended location, the sea deeper than 100 meters and not deep for installing mooring line. And in this case, the water level is constant since there is no tidal wave. The figure shows the recommended area selected by the previous slide. We select the target area that overlaps the 3 areas. The right slide shows the selected area, and this area can be stable for the wind and tidal and not distribute the ships moving. Next is a mathematical model for our design. For the mathematical model, we divide two components to consider. The floater is the floating part on the marine surface, and we consider the density, height, and volume of the island. The marine line is the fixed part of the floating city and has many factors to consider regarding material property and structure, but we simplify this to the simple spring model for the simplify our mathematical model. We have the as the midterm presentation, we have defined the mathematical models for the floaters. The considerable factor is wind, height, and the current on the floater. In this figure, the moment is the main factor to consider stability, and this moment can occur by the wind and current flow. In this situation, the height needs to design lower for the moment of stability, so we need the mooring line for the height floating island. So we add the mooring line to increasing the floating island stability. We can consider many factors that make the tide on the floating island, and mooring line can decrease by the spring and damping moment effect on this. In this project, we define the mathematical model for mooring line for the stable floating city. The model is as follows, and white comment is our process for our design mathematical model. We assume that the mooring line is the spring and connects to the floater and the bottom. First, I will show the process for our model. First, we have to define our city rate for the design height. Next, determination of design degrade of floating building. Third, checking of stability of floating house. Fourth, calculation and check of mathematical height. Finally, checking the hill angle of floating house caused by possible crowding on one side of floating platform. This is the mathematical model for the previous slide. We focus how define the stable structure and what height we needed. And also, we can define the angle which made by the wind or current and figure out the relationship between the angle and the height. However, there are many challenges to calculation with only a simple mathematical model. We can divide the design factor for the floating island to island structure and environment. In floating island, we need to consider not only structure effects like total density or volume and simple mooring line to the spring, but also we need to consider material property that prevent crack by the moment made by the wind or current. So we need simulation for accurate. We need simulation to define for accurate model. We have to define the model for the simulation. So we figure out the example for applying on the simulation. There are three types of mooring line for the floating wind. And some property like stability and deployability for our floating island larger. On the floater, there are many types is applied on the floating island, so we need to think about stability, and also after we build our floating city, we need to make other structure for expand our floating city. So we consider about the developability for our floating island. So we select the same stuff for our simulation. This slide is for the suggestion of our floating island simulation method. The vector for the simulation is as follows. First is the environment setting. We put the environment like the wind and the flow in the EC and the floating model to the sensor. In the input parameter, we put the design vector on the floating city like structure, mass, chain properties, and chain length. In this parameter, when we put this input parameter to the simulation, we can get the output parameter and we can gather some information for our structure stability or chain defect. And by using this information, we can define our floating island structure and battery. Summary is as follows. The floating city location is selected on the EC and we choose the recommended area for install. And we define the floater and mooring line structure and construct the simple mathematical model for floating city. And we select the mooring structure for the floating city and we suggest the simulation method for our design the floating city on the EC. Thank you for this.
Some other team members? Oh, yes.
We was hard for simulate because there are lots of information for input, so our computer can gather the information. So I just put our suggest method.
No, that's it. Right. Any other? No. Okay.
So I trying to calculate the separate one, which one is mooring line and the another one is float.
Yes, we just model developed to floater to the mooring line structure.
So you suggested the method to calculate the stability of the city, and it is combined with the floater with mathematical equation and mooring line with computational calculation, right?
Yeah.
So, yes.
You consider the extreme weather conditions like
we cannot define their external vector in the simulation. So in future work, we have to input that kinds of situation for our simulation.
Yes. So you told me that you have two separate calculation steps. Which one is floater and another one is mooring line. So which do you think has more severe condition? Which one is more difficult to meet the sea condition?
Maybe mooring line is more difficult for our sea condition because the mooring line is our target is the over the 100 depths of our sea level, and maybe the chain of the mooring line is very long. So in this case, the mooring line property or length can be considered. So we need to consider better property and stress and strain for our chain. So there are more design factor on the mooring line.
Thank you.
There's going to be a question not be long because of the interest. I think we could have also taken the approximation of it. Right? So what you need to think about is what is the height of the rate, not the length of the reason. Why did you not simplify the American problem? Like, why did you try to consider all the factors in the And besides that, I think we can also provide the detail and the quick plan about the simulation, like which numerical method we're going to use for. Not provide it.
It will hard for us to simulate because our team member or first for
Well, team member. Team member? Not here?
or for first simulation, so we have difficulty for how to start our simulation. So we just have define how to simulate and how we apply mathematical model. We just do things, and when we input the data, the program is not start at all. So we can put some simplified data for our group.
My comment or question is, who can be the customer of that building? Who will stay at the building? And how many people? Because you are only talking about East Sea, but it is far away from the land or city, then you need to have a transportation to the building. So it is not convenient for them. So you should think about the customer who will stay resident of the building. That is one simple starting problem. Is another stability of high-rise building. This 10 is stable now. If you increase the height 10 times or 20 times, the stability is not good, even in the land side. But if this is a floating, stability is much worse of high-rise building. Then you need to have a very strong mooring lines. That's why I commented the other time that there is another team who is designing underwater habitat. Which term is it? Underwater living habitat. Then you can combine those two items together, then it will be good for stability. Because underwater body is big, and high rise is okay. Okay, it's time. Thank you very much. And then we move on to team 8. Rosalind.
Again, where's the presentation mode? I'm sorry. No, presentation.
Okay.
Thank you. Okay, so, hello, I'm Rosalinde Borek, and I'm the final presentator of Team 8. And our project topic was Back to the Future, using wind energy for modern ships. First of all, I will give you like a brief reminder of what our project was all about. And then we will finalize our ship model. And with this specific ship models, we then do some environmental and economic modeling, whether or not using wind power is feasible for this specific model. Our project objective was that in history, the main energy source for shipping was wind energy. And it then got replaced by fossil fuels at some point, but because of reason everybody's probably aware of, we should now try to use less fossil fuels than before. And our idea was that maybe we can try to go back in time and use wind energy again. And for the timeline, we are now at our third and final presentation, where we wrap up the project by finalizing the model and calculating our results. This was the status of our project at midterms. And as it goes when you develop such a project, sometimes you have to go back and make some changes. So let's see what has changed since midterms. We decided to stay with the same category of ships. We wanted to stay with large ships. The application also stayed the same, but we made it more detailed by deciding to go with a carrier ship, not with a container ship, with the simple reason that the carrier ship usually has more space on deck to put structures on it that can utilize wind power. Then for the route, we had to make some changes. Also, like it was mentioned by the professor last time, that we have to make some changes there. So what are actually the criteria for choosing a good shipping route for a model like this? First of all, we want to use wind powers. Therefore, we have to have a route where we have wind. That we can use well. And also it needs to be a route where we know that we will have wind, because we want to work with we cannot build a whole ship and send it off and then see if we have wind. No, we need to know that we have wind there. And some studies also showed that usually for ships trying to utilize wind energy, it's usually more efficient if the route is on the same hemisphere and doesn't go across the equator. So that was also a criteria. Then, of course, the ports have to fit the ship size. Since we are going with a large ship, not all ports are big enough for that. And then the route should also have a use case for our ship size and our ship type. We then decided to go with a shipping route through the Mediterranean Sea, because this is a route where a lot of ships, a lot of different size and different use pass through, including those of our use case. And more in detail, we then choose a route which goes from the site in Egypt to Dunkirk. Sorry, I'm probably totally butchering that name, in France. And it has a total distance of 3,700 kilometers, and with a traveling speed of 13 knots, which is a little bit on the slower side for such a vessel, but makes using wind energy more efficient. The ship would then need 13 to 15 days for a route like that. So that's the route done. Then anything that's still open is the renewable energy technology. There we also decided that we wanted to do some changes. We originally wanted to go with rigid wing sails, but we then decided to switch it out to Flettner rotors. The biggest reason for that was that the Flettner rotors are an older technology than the rigid wing sails, which also means that it's a more well-known technology. There has been a lot of more research done on Flettner rotors compared to rigid wing sails. And for us, it was then, of course, also easier to find the literature we needed for this project for the Flettner rotors. We also decided to go with a retrofitted ship, which means that you take a ship, a normal ship with a normal ship motor, and which might also have been in operation already for a few years, and then put Flettner rotors on top. And the reason for that decision was that way we have a good comparison of the same ship with or without Flettner rotors, as in if we would have compared like two different ships, one with and without, the comparison would might have been a little bit more difficult. So yeah, this is our final decision of our ship model. And those are the specifications. Since none of us is an expert ship developer that can just make up some model values that fit together from scratch, we decided to base on our specifications on a real life vessel, which is the Wadi Al-Kram, which is a large carrier ship that is often going on a similar route than the one we chose. And now that we have our ship model, we can finally try to answer the central question of our project, which was, is using wind power worthwhile on modern ships? And for that, since we decided to use Flettner rotors, we first need to figure out how much propulsive power can a Flettner rotor give to a ship. The Flettner rotor works in a way that we have a large tube, and that tube gets turned by a motor, and through this movement, the induced wind then creates a drag force and a lift force and the resulting propelling force, ideally in the direction of the ship in which the ship is moving. To calculate this effective power is relatively straightforward. The most difficult part is lift and the drag coefficient, since those have to be calculated by numeric modeling. So this is the most difficult part about this. But if you have the effective power, you can then calculate the net output power of the Flettner rotor, because as I said, you have a motor that is turning the rotor, so you need to subtract the power you need for that motor from the effective power to get the net output power, and then also take the efficiency in mind. Now we have the values for one rotor. Now we need to decide, okay, where do we want to put the rotors and how many do we want? There you have to take in mind that the crew must still be able to move around the ship, and operations, maintenance, loading and unloading still need to be able to be conducted. For Flettner rotors is quite much. Real life examples we saw often use less because there's just not more space. We still decided to go with 4. We also decided on North Power Rotor, which is a company which has some experience on constructing such rotors. And then what has to be kept in mind that since the rotors change the airflow around them, if you have multiple rotors close to each other, they will affect each other. So here, as an example for the apparent wind speed on some values, you see that on each rotor, you have a slightly different apparent wind speed and direction where this comes from. So this has to be taken in mind, that you cannot just calculate your effective power for one rotor and then multiply it by 4. You need to model it for every single rotor. And again, this is needs highly numeric simulation, so it's not that straightforward. But if we then have know how much propulsive power we get from our Flettner rotors, we can have then with that also the value how much propulsive power we save from the main engine, from the diesel engine. And with that, we can then also calculate the amount of fuel that we save by using the Flettner rotors. And if we have the emission factors for our specific engine, or in this case, using literature values for a marine diesel engine, we can then also calculate the emission that are saved by using the Flettner rotors. And since we are saving fuel, we are usually also saving cost because fuel is expensive. There are a lot of parameters also have to be taken in mind because the fuel costs change over time, so then it doesn't take the same. So this is also a little bit of a guessing game. Also values like the interest rate have play a role in this, the initial investment you have to take to put the flattener rotors on top, which also can change depending on different parameters have to be taken in mind. So the economic values is always a very subjective value and can change drastically if you change the parameters. But now finally, those are our results. The average net output power for all of our four rotors is roughly 1,500 kilowatt. It is very important to note that this is very much dependent on the wind speed and the wind direction. So this can change a lot. Like if the wind comes from the wrong direction, we can end up with 0 net output power because it's just the wrong direction. But those values are average values for the shipping speed of 13 knots. Then if we look at wind data over the whole year on our route, we can get average annual fuel saving of around 1,600 tons per year, which is roughly 22% of the complete fuel needed. We can also see that there's still a lot to go if we want to make a ship only work on wind energy, but still 22% is already a lot. And since there's also important to say that since wind changes and wind is also changing with the season, those values are also highly depending on the season. Usually in January, you can save a lot more fuel than in October because this is just the wind in the Mediterranean Sea. But if we take this average annual fuel saving, we can then calculate the annual reduction in CO2 emissions, which lies by roughly 9,000 tons per year. Just for scale, a typical passenger car emits around 4.6 tons per year. Of course, there are a lot more cars and ships, but just to get a feel for those values. And then for the annual fuel saving costs for an annual interest rate of 5%, you could potentially save around $1.3 million, which is also quite a lot, but it's again said that this is highly dependent on a lot of different values. And I think to look at this table, I think it's safe to say that for certain routes, for certain examples, yes, it is already feasible to use wind energy for modern ships. To not use it completely, there's still other energy you needed for help. But I do think that even from today's perspective, it already makes sense to do this. Then this was our team 8, and the tasks we did for this final part of our project. And then I'm done with my presentation. Thank you a lot for listening.
Any questions from other team? No? Yeah.
Few comments and questions. First of all, it was very interesting and I think the design concept and design basis are well defined and very structured. And I had some questions. The feel of this ship is it what?
It was ship design.
Ship design. So that was the question, and you said that it could be very variant or variant. There might be very variant fuel saving with the season and wind direction and speed. So it would be better to show some more cases about the wind cases. So you said that VA strength 12 meter per sec, one cases, one case, but it would be more better to show more. And here, okay, skip. Thank you.
Thank you.
How many ships? Would you like to-
No, I don't know exact numbers. It was very hard to find that out because a lot of times when we were looking stuff up and we were like, oh yeah, there's a ship, and then we would look at it and we're like, oh no, it's only in developing phase. It has not actually been built yet, and like to figure out, okay, like to actually find sources of yes, this ship already is on its way with its Flettner rotors on top, and this is the value, was very hard to find. And so we also don't have exact numbers of how many ships already have that. We were able to find some examples, but yes, the research was not that easy on that.
It is not a possible choice to know what are the side effects.
So sorry, what?
What are the side effects?
The side effects. Yeah, we like for the calculations we did, we mostly assumed that the rotors won't have any impact on things like stability and other stuff. Just because everything would have gotten a lot more complex with that, and we were not able to do that. But those are things that have to be taken into account. Also things like they are quite high, so if you have to go under bridges to get to a port or something, this is also important. I have seen some examples where the Flettner rotors were able to put down, like put out. So yeah, we briefly touched on those side effects things, but then decided for simplification to not take them into account for our model situation.
One question. Even though the you're saying the ship emissions reduce emission, why not popular?
Similar question. Right?
Yeah, I think that it's still very new. And what I also think is that the space is really a problem, because I think that especially like modern merchant ships, they have to be like very efficient to take like as much payload as possible to get somewhere to be so that to be cost efficient. So I think that in a lot of cases it's hard to find the space on deck of a ship to put something on top.
Similar. But good thing is you respond to previous comments to select the route and ship type. But still remaining question is why you choose that route? Is there any reason for that between Egypt and France? And then additional question is what kind of cargo you are trying to carry with that ship and route?
We actually didn't thought about the cargo. That was a thought that we
didn't
didn't
see
make.
that there's a sample ship name.
Yes,
That ship maybe
we could have just looked it up. It would have been very easy, but we just didn't thought about it. I think.
what type of cargo the ship is carrying?
I think it's mostly coal and grain.
Good.
I thought I've read it briefly. I thought it was like coal and like grain similar
bulk
cargo.
carrier.
Yes.
But bulk carrier needs to have open the opening to unload and load cargo, so that maybe interfere with that rotor.
Yes, the way it looked like was that there were like different compartments for the loading and unloading, and it was not like the whole opening that was completely open. And
That's why I'm
like,
asking
yes.
what type of cargo you are trying to think about, because depending on the cargo type, if the ship is for oil tanker, then it's simple.
Mhm.
Only pipe is connecting. So you don't need to open the. So the final second question is similar to them because you are trying to set up a new device to lower down the fuel consumption, but there is a cost for retrofit or modification. If the cost is very high, 10 million, then fuel saving is so you need to consider together the investment or modification cost together, the saving and additional cost. That is unique color. Probably that is the reason why that chip is not popular yet. Don't know. But if the technology is going up, the efficiency is going up, then cost to maybe economy better
Hopefully,
in the
yes.
future, right? But I'm saying you need to consider together.
Yes.
All right. Thank you very much.
Thank you.
네, 하십시오. 이게 딴 거. 내가 해줘? 쉐어를 바꿔야 돼. 이거 공유 준비를 했다고 다시. 일단 시작을 먼저 해보고. 알아서 하십시오. 자. 네.
Okay, good afternoon, everyone. I'm Seungwon Lee. I'm the first presenter of Group 9 final presentation about autonomous monitoring system for microplastics in the ocean. And Haesung will be the second presenter of today's presentation. So I will show the current microplastic sampling method.
This protocol describes microplastic sampling and sample analysis on the sea surface. Sea surface sampling. Deploy the MantaNet from the side of the vessel using a spinnaker boom or A-frame using lines and carabiners. Deploy the MantaNet out of the wake zone in order to prevent collecting water affected by turbulence inside the wake zone. Write down the initial GPS coordinates and initial time in the datasheet provided. Start to move in one straight direction with a speed of approximately 2 to 3 knots for 30 minutes and begin the time measurement. After 30 minutes, stop the boat and write down the final GPS coordinates, the length of the route, and the average boat speed into the datasheet provided. Pick up the MantaNet from the water. Rinse the MantaNet thoroughly from the outside of the net with seawater using a submersible pump or water from the boat water reservoir. Rinse in the direction from the manta mouth to the cod end in order to concentrate all particles adhered to the net into the cod end. Note, never rinse the sample through the opening of the net to prevent contamination. Safely remove the cod end and sieve the sample in the cod end through a 300 micrometer mesh size sieve or less. Rinse the cod end thoroughly from the outside and pour the rest of the sample through the sieve. Repeat this step until there are no longer any particles inside the cod end. Concentrate all material on the sieve in one part of the sieve. With the use of a funnel, rinse the sieve into a glass jar or plastic bottle by using 70% ethanol.
2007년 아르헨티나의 수도 부에노스 아이레스.
Hola, ¿todo bien? Sí.
So as you see this video, if we want to sample the water, we have to go directly to the exact location where we want to sample the water. But if we use the ROV, we can increase the range of sampling. And so by this, we can save the time and fuel for moving this kind of ships. And also we can increase the range of the space for sampling the water. So our goal is designing a remotely operated vehicle that can sample ocean water in order to measure the concentration of microplastics. So here are the feedbacks that we got last time. So first one is, why do we choose shallow waters? Because microplastics accumulated most closer to shore due to the urbanization. So I will show the materials about this feedback later. And second one is about the research on concentration of microplastic and sampling data. This will be also talked about next slide. And last one is about money problem if we are going to do repeated samplings. So our group target is the automation of monitoring the microplastic sampling. So in the long term, cost will be reduced in the long term because the testing and measuring process can become automation. So this is the research on microplastic concentration. So in the left figure, the first figure is about the number of the microplastic per square kilometers, and second one is about the mass of the microplastic. The dimension is about gram per square kilometer. So as you see this figure, lots of microplastic can be found near the land sites. For example, like Australia and Japan and USA. So, and second figure is from the Adventure Scientist updated map of global microplastic collection data. As you see this figure, we can also find that the microplastic are accumulated near the land site. So our specific sampling location will be the near the Korea Peninsula. The first figure is about the fish species living around the Korea Peninsula. So there are lots of fish are located between 0 to 100 depths. And the second figure is about the example of the fishing ground. So our specific location is around the Korean Peninsula, and depth will be the 0 to 200 meters. And second specific location will be the Hamgang and Paltang Lake, because Paltang Lake is the main drinking water source of Seoul and Gyeonggi citizens. And in Korea, half of the people are living near the Seoul and Gyeonggi citizens, so we are focused on this area. And so following the research, the depth of Paltang Lake or Hangang will be the 3 to 24 meters. So the depth will be like this. And second table is about the list of companies emitting plastic waste near the Paltang area. So there they emit a lot of plastic waste around the Paltang area. So there will be the demand for measuring the microplastics near around this location. So next slide, the Hae-seung will cover the rest of the materials.
Hello, I'm Hae-seung, otherwise Ezekiel, and I'll be presenting the second half of our presentation. So once again, we're primarily going to be using ROVs for our sampling. We're still going to have it tethered to a main ship in most cases, especially because we're going to be in shallower waters. It's easier to use that tethered connection to maintain a connection and to maintain control, as well as provide power to the ROV. If we do end up expanding further, if we go to deeper waters like the inlets of the river or further into the ocean, you could switch over to battery-operated ROVs that use optical communication instead. So, as you saw in the video, the surface sampling method for microplastics is somewhat involved. People have to manually collect the plastic and manually filter it. And we're going to discuss the methods for how we analyze the samples later, but our methods allow us to use liquid samples. So we can use a cylinder connected to this ROV to collect vials of water instead. And our testing methodology also allows us to test sediment as well. So we're going to use a similar vial for seafloor sediment. So to recap the microplastic testing methods we had discussed last time, the important one here is going to be FTIR spectrography, which uses infrared radiation to determine the chemical makeup of any given sample. FTIR spectrography works with both solid and liquid samples, which works well for our use case. There's also gravimetric analysis. This is a much more involved method, but it's usually more accurate, and it's used by other sources as well. You separate out the solids and the liquids. You use chemical processes to differentiate the materials as well as sterilize it. You collect those particles, and from there you can measure it directly. So our testing methodology is going to be in 2 steps. The first one is FTIR analysis, which is going to happen locally on the ship itself. And we're going to focus on scale with it. So we want to collect as many samples as we can get and test them quickly to get a wide scope of data. Unfortunately, this is going to be operated under very unoptimal conditions. Ideally, you would have more time to sterilize and process these samples before you test it. But we're accepting that we're going to have a little bit of inaccuracy because of our second step of using gravimetric analysis. In this situation, we can focus on accuracy by reducing the amount of samples. We're going to only test the important ones, so outliers, trend breakers, and areas of interest, so areas where we notice a high amount of pollution. And this final set of data is much easier to compare with other research. So this is just a diagram of where our samples are coming from and where they're going. So we collect water and sediment samples, with all of which get tested with FTIR. And so those 3 areas of interest, outliers and trend breakers, will go to gravimetric analysis. And the other ones that fit within our trends, we can just discard and not have to worry about storage or transportation, which once again makes it easier and cheaper. The main reason why we're going with gravimetric analysis for our important samples is because it's the method offered by the NOAA Marine Debris Laboratory, which means that it's much more directly comparable to other data sources and can be more beneficial to the wider community. We do have a couple of challenges that come up with this sort of implementation, one of which is the range. One of the benefits of using automation is that you can cover a wider scope, than if you manually collect samples, but we are limited to the length of wire or the battery capacity of our ROVs. Also the issue of the upfront cost. These testing equipment and ROVs are not cheap, but we're hoping to offset that because it's a one-time purchase, and this is a system that can be repeatedly used in the future to hopefully reduce the overall cost. And especially if we're focusing on like a river or certain environments, these ROVs might not be capable to withstand all environmental factors, so we do have to be careful about when we're testing. So to just go back over our final plan, we have our ships with ROVs for sampling, all of which undergo FTIR locally. We have all the data, and select samples will be sent to a data center where it can undergo gravimetric analysis, and that final data can be compiled and analyzed. And those are our references. Thank you very much.
Two questions. You told us that you're going to get water sample from 3 meters to 24 meters. So is what location the microplastic accumulates a lot in the ocean? So 3 meters to 24 meters, is it feasible range for sampling the microplastic?
So different microplastics have different densities, and so you'll see different concentrations in different depths. Right now, we specifically chose to focus on drinking water because that's where it's most applicable. And in that case, 3 to 24 meters should be plenty of data. If you go further out into the ocean, you probably do want to go deeper to get different samples as well. But for immediate application, 3 to 24 meters is enough.
My second question is that you mentioned the challenges of ROV. The third one said that Han River has very strong current, so it would be a little bit difficult to operate ROV. But in case of ocean has much more stronger current than Han River. So this machine, I'm a little bit curious whether this machine can operate in the ocean.
The type of ROV being used would probably have to differ if we go into the ocean. Once again, if we're focusing on a river, we do want to reduce costs even a little bit by going with a perhaps less powerful ROV, but one that's more reasonable for a river. If we go into the ocean, you probably want to invest in a better one.
What aspects can be approved? What aspect can be improved for ocean operation?
I think we have to use more deeper one because if we use smaller size of our it could be affected by strongly affected by the ocean flow, some kind of thing. So I think we have to increase the size of the
Right. This is nice to see, including the Paltang drinking water case. And also good to see collaboration among team members. One thing you need to think about that is Paltang is a reservoir rather than river. There is no flow. Very slow flow. It is a lake, deep lake. But you need to think about it is a
very different situation from the ocean place. So that you need to separate out the cases, including Paltang is very nice, but you need to think about separately the ocean case and Paltang. Environmental and also plastic maybe much different. And for the coastal region, shallow water, the current is not so strong, usually. So one thing you should see that in yellow, the west coast, the tidal current is strong, but that is only between specific time zone, twice per day, right? That is a strong case. Maybe you may have a sampling time differently. When there's a no current, has a current, can sample it. Otherwise, all right. Thank you very much. Then team 10. 시계리 하는 거 알아? 몰라? 네. 네, 해줘.
Okay, hi everyone. Our topic for the presentation is marine debris collection system, and I'm today's presenter Da Kang, and we have Lu and Jian for our team member. So this is what I'm gonna tell you on today's presentation. Yeah, so let me briefly review our project. So our project was about marine debris collection system. So by comparing several devices during the midterm presentation, we thought that the ocean cleanup system would be the most proper system to our case. So we wanted to apply this system to South Korea by selecting the area and scaling our device. And this is the feedback and the comments from the previous presentation. So to answer each comment, we added related information to those specific pages. And if you look at the timeline of our project, we wanted to focus on those things on the final presentation. And then I want to talk about the location first, because we got the comments from the previous presentation saying that we need to precisely select the location to effectively remove the marine debris. So if you look at those images, these days there are lots of news criticizing that the marine debris near Songyang Yokjido. And if you look at the graph below, this shows the amount of marine debris at several locations all over South Korea. So the marine debris near Songyang Yokjido took off 40% on 2021 and 60% on 2022. And then we wanted to search about the geometries and the conditions there. So by taking advantage of the tidal flow there, we wanted to remove the marine debris more effectively. So we chose the area inside the red circle because this is the area where the most tidal current flows. And then I want to talk about the debris size and the types. So most of the debris near Songyang is macro-sized debris, and they are mostly composed of the plastics and the papers and timbers. So using those informations, we wanted to scale our device. So as an input values, we use stretch size and the distribution and tidal flow and etc. And we wanted to decide our system's net size and depth of the net and period of usage and dimensions and how much marine debris we can collect at a time and how much effective power do we need to operate our system. So the first one is about net size and the depth. So as I mentioned before, since most of the marine debris, there are macro size debris, which is larger than 200 millimeter. We decided our net mesh size as 200 millimeter. And since most of the debris are timbers and the plastics, they are located at the depths less than 2 meter. So we decided our net depth as 2 meter. And next is about our device dimensions. So by looking at the example of how other people use this kind of system to the real case, we decided our system dimensions. So when the people use system 0.3 to the Great Pacific garbage patch, the length was 2,500 meters. And by considering the fact that the area was 1 million square kilometers, and they use 10 full-size systems, we decided our system length as 11 meters by using that equation. And then next for the accessories, so we're gonna use the circular float ring to allow the entire system to float. And we wanted to use the as much float rings as possible, so that because the more buoyancy we have, the more marine debris we can collect at a time. So 30 circular ring for the retention zone and 64 for along the length of the net. And then we wanted to use 10 cameras to monitor the marine life and 30 green LED lights to be visible to the wildlife and the boats, even during the bad weather. And next is about buoyancy system. So we wanted to calculate how much marine debris we can collect at a time. So using the above equation and considering that the buoyancy of a circular ring is 1.7 kilograms and the mass of the accessories are like below, we got 115.8 kilograms. However, we cannot fully load the net, so we assume the efficiency is 50%. And the next is about propulsion system. So to calculate how much effective power do we need to operate our system, we use those equations. So the effective power can be calculated by multiplying the total resistance and the velocity. And the total resistance of a ship can be calculated using that equation. So when we know the ready surface area and the sailing speed and the mass density of water, calculating the resistance coefficient is very important. And this is composed of the viscous term and wave making term and air resistance term. So for the viscous term, we can calculate it using that theoretical equations. However, for the air resistance and the wave making term, we don't have any theoretical equations. So by referencing the literature, we assume the air resistance term as 0.407 because we're gonna use the small ship. And for the wave making term, we reference this graph. And we assume that we're gonna use the Korean fishing boat. So using those values, we firstly calculated the effective power without considering the wave making resistance and also float number versus ship speed. And then after that, we calculated the effective power considering the wave making term. And then if you look at the left those videos, this shows the current and the tidal flow change within days. So when the current speed is up to 2 knots and the boat forward speed facing the current is up to 2.5 knots, the absolute boat speed should be up to 4.5 knots. So we presume that during driving to the removing side, we need around 250 horsepower, but on operation, we need less than 15 horsepower. And then next is about period of usage. So during the winter season, the wave flow direction changes regularly once every 2 days. However, for during the summer season, the wave flows with constant angle. And since there are heavy rains that makes more current flow and debris movement, we thought that summer will be the effective season to collect marine debris. And by considering that we can collect 55 kilograms for one time, and we need to collect 800 kilograms a year, we thought that we need to at least operate 20 times. And then we simply calculated the economical expectation. So by referencing the left GDP table, we calculated the estimated costs on each businesses. And then we, one thing you can notice is that we multiplied by 0.5 because only around 50% of the marine debris come from Tongyang. So this is the job allocations for our team members, and thank you for your attention.
Listen, members. No. Okay.
Why are there so many?
Louder.
Why are there so many?
I guess it's because of the flow that starts from Nakdong River. I think most of the debris are accumulated on that area. I couldn't find the exact reason, but by referencing the statistical data that I showed you before, we chose Tongyang area.
You calculate the resistance for the ship to calculate the size of the propulsion system. So as the ship operates, the debris will be collected. So debris can add some more resistance to the ship. So it can be more it can be better to consider some resistance from the debris.
Oh, right. We couldn't consider that part. Yeah.
Just sort of similar. It is only empty net. There is a resistance, but with including debris is collected, the resistance is increasing as debris is increasing. Right?
Yeah.
So it is depending on the how much of the debris. So it slowly increase. You need to think about or consider the kind of situation. But anyway, it is good to see very specific problem and solution. One comment is that I don't know, I can't remember, but you already choose as a net as the device. When did you decide to choose the device as a net rather than other? There was a different kind of method, right?
Yes.
At the beginning.
Yes, right. During the midterm presentation, we showed different types of the marine debris collection system, but for like to take advantage of the tidal flow and to set the system into the sea, we thought that choosing using this kind of net system would be
So you
better.
already choose from the midterm
Yes.
presentation. Then you need to explain the previous decisions.
Okay.
So recapping for audio. Yeah. All right, thank you very much.
Thank you.
이건가? 네. Hi, this is Sangyun from Team One, and I'm gonna tell you about the perfect location, decision-making process for tidal power plant in Korea. So these days, half of the population of Korea living in Seoul, Gyeonggi, and Incheon, and the three city is gathering in north-south, I mean north-west of the Korea, and that kind of population gathering, of course, needs energy to live them, and because of the Seoul being a mega city, they need more energy from a near area. But in Korea these days, most of the energy is from the fuel cell. Fossil fuels, and some parts of the energy is from the nuclear energy, and most of renewable energy just supporting that energy parts. So because of the carbon zero and Korea plan to decrease 40% of carbon to 2030, we need renewable energy and sustainable renewable energy for mega cities like Seoul, Gyeonggi, or Incheon. So because the three sides of the Korea facing the ocean, we plan to find out some renewable energy from the ocean. So that's why we decide the tidal energy for new generation renewable energy. But there's lots of renewable energy we familiar with. So onshore wind, offshore wind, solar is the most popular renewable energy, and they are very cheaper energy, but they are not sustainable and predictable. If the cloudy weather, solar energy cannot be generate any energies. If the wind stop, wind energy also cannot be get generated. But tidal energy is more sustainable and predictable compared with the other renewable energies. But the one issue is the cost. Tidal energy's cost is very high compared with the other renewable energy. As you see this table, most of the energies in 2018 decreased similar with the cost range of the fossil fuel, but cost range of the tidal technology is way much higher than other renewable energies. But when you see the middle two things like solar energy, their cost is dramatically decreased through 10 years, like 8 years. So in 2010, the solar energy's cost is similar with tidal energy these days. So I expect that tidal energy cost can be decreased after 10 years. So it can be competitive enough in a cost perspective. This is the common, well-known graph that showing the cumulative industry development and the cost. LCOE is the one big factor, directly related factor with cost of the renewable energy. And when the industry develop and getting bigger and bigger, their cost getting smaller dramatically. So these two factors, this graph and these factors can show that tidal energies will have a competitive cost after maybe 10 years. So that's why we target on the tidal energy. But yeah, it's very powerful and predictable energy. But also it's very depends on tidal differences. So it's really important to decide the location to place the power plant. So that's why we picked this topic for our TOM project. This is the schedule. Because we discussed lots of things in proposal and midterm presentation, this final presentation will focus on the decision-making process. Before we
making the criteria. In Europe, there's lots of tidal power plants. So we search about the criteria from Europe. There's 5 big issues that when they decide the location of the power plant. First is tidal range. Second is geometrical condition. Third one is water depth. Fourth one is environmental. And fifth one is infrastructure. So these kind of things can be should be considered for location decision. First, it's supply and demand, and it's also related with the infrastructure. As I mentioned, that Seoul, Gyeonggi, and Incheon getting bigger and bigger and becoming a mega city. They need more energies. In case of Seoul, they only generate 8.6% of energy they use. So more than 90% of the energy they use is from other cities. Also, Gyeonggi, they only generate 60%, around 60% of the energy they use. But 95% of the power loss occurs during the transmission. So there is a high demand for eco-friendly power generation on the West Coast to replace thermal power plants, like fossil fuels. This is environmental factors. We need to care about 2 things: the tidal differences and eco-friendly things. So the left picture showing the tidal differences. So the Incheon and Gyeonggi, their tidal difference is around 8 meters. Every annual average is 8 meters. And Chungnam, they have a 6 to 7 meter tidal differences for annual average. But we need to consider about the environmental things. So the middle picture showing the protect area. It's forbidden area to build something power plant or some kind of industry things. So we need to care both of things. And third one is related with the amount of generation of the current. So these factor is very complicated to figure out. So it's from the simulation or experiments. Because of that complexity, these factors is from refer to that literature. Based on that literature, region 1 and region 4, Incheon area, Incheon Gyeonggi area, and Chungnam area is the most appropriate. The proper area to build the tidal power plant. But based on the Seoul, Gyeonggi, and Incheon's energy using, it's way much higher than Jeonnam. So we decide this area, this region, is the proper area to build the tidal power plant. Thank you for your attention.
Okay.
No question about the main content itself, but I have some other questions. First is, why is tidal energy so expensive? Is it because of the low energy conversion efficiency, or is it because of the construction and maintenance cost?
Actually, the maintenance cost is not really high. It's higher than wind or solar energy, but it's quite good. But the construction part, it's way much higher than other renewable energies. So that part, it's highly related with the technologies. So it can be reduced as time goes by.
And my second question is that you said that about 95% of the energy is lost during the transmission. Is that the number we should invest?
I mean, yeah, it's true, but 95% of energy is lost, energy, not energy, 95% of energy loss. I mean, this energy is lost like this when you're using like this, and 95% of this amount.
No.
Your results say that Vision 1 is the best solution. Then, did you consider the electricity transfer with high voltage transfer line?
Actually, it was our additional goal, but we didn't make that here. But yeah, we didn't discuss about in this presentation.
So regional generation is only considered.
Transmission. I mean transfer. I mean electricity transfer issues can be discussed later.
Right. Let's see the slide before what happened. This one. The picture. This one. From this picture, I see tidal power generation has a two types.
Yes.
Right? One is a dam type, the other one is open channel type. Right? This looks like open channel type.
Yes.
Right? But at the conclusion side, you say it looks like a dam type.
No, it's a open channel type. As you see here, shallow depths has the advantage that have the cost of construction can be decreased. So that's why I pick near the water nearby the land, and also the.
Can I see the map? The final map. Right. So it looks like a dam here, right? You choose location here.
Yes.
It looks like a dam. You need to have a dam. So you are saying you need to locate the open channel tidal power under the seabed or waterbed there.
Yeah, that's
There
our
is
type.
But you don't know the tidal flow there, speed. Tidal flow speed.
Actually, I didn't put that in slide, but one of our references showing actually
it should be very slow because of the land, right? Tidal height is big,
yes,
but speed is slow. So the current, the flow rate speed is very slow.
So it's better to
So
make
that
the dam
location
type.
is dam time is problem. Can I see the map? Oh, here it is. 울돌목.
Yes.
울돌목 is between island and mainland. So that flow should be flow between them. So that there is a very high speed tidal flow. Open channel should be located around that kind of 울돌목. Not toward the mainland side. Between land and island or street, so that sometimes there is a very high flow, twice per day. Ultolmo is very typical case. The different question.
So it's better to change the
You need to check the statistics of current speed there. Another location can be Ganghwa-do.
Yeah.
Ganghwa-do, between Incheon and Ganghwa-do, there is very high speed of current. That's why 13th century, 14th century, there was an invade from Mongolia, and the king of Goryeo, right? Goryeo is escaped to the Ganghwa-do because the water is very narrow, but flow is very high there. That's why Mongolia cannot invade to the Ganghwa-do. That is another. But anyway, you need to investigate the speed, high speed regions of the current speed.
Okay, thank you.
All right. That's enough for today, right? You answer. Oh, one thing is that on Thursday I'll be online.
But you need to come to here. TAs will be there, right? And everything is same, only myself will be online. Thank you.